Welcome, sir.
Thank you, ma'am. Thank you for the kind words.
Thank you, sir. Now I would like to hand over this session to Dr. B. Dasagiri Reddy garu. Welcome, sir.
Yeah. Thank you, everyone, and good morning to all. Firstly, I would like to thank HOD and organizers for giving me this opportunity. And today we'll be talking about solar PV, starting from very basic. So let me share my screen first, and please let me know when you can see my screen. Is it visible, ma'am? Hello?
No, sir.
Hello?
No, sir, it's not visible, sir.
Sir, can you share your presentation, sir? Pin on presentation, sir.
One second, sir. Hello, sir. Am I audible now?
Yes, sir. It's audible.
Okay, sir. And I hope now you can see my screen.
Sir,
I think I don't
can
have the
you,
permission to share the screen.
no, sir. You have, sir. It is showing as you're presenting, sir. So can you present your whole
Okay.
screen, sir? Entire screen.
Yeah, I'm doing that. Okay.
Now it's loading.
What
Yes,
you
sir.
can see?
Sir, it's Meet. It's a Meet window, sir.
Okay. The slide will be coming
Yes.
up.
Now it's coming, sir. Yes, sir.
Okay, sir. All good? Hello? So sorry for the mess, participant. So we'll start in a while. So today we'll be talking about photovoltaic technology and systems. So we'll start with the basics of sunlight. Then what is the property of sunlight? how we are able to get the energy. Then we talk about selection of material for PV panels, and then we talk about how it works exactly. Then we enter into what happens if there is a mismatch in cell. What about partial shading? Then we talk about systems. Okay, so it will take roughly around 4 to 5 hours, but I'll try to stick to the time given by the organizing committee. And for the benefit of participants, so I don't want to enter into the general knowledge, like how many installations are there in India, in or all the world, what is the futuristic view of solar. I'm not going into that. We'll be directly jumping into the topic. So this is the overview of my presentation. So I'll be talking about what is energy, energy conversion, then solar energy, what is the properties of light, then based on that, how we have to decide on the semiconductor physics. Then we talk about diode operation, then solar cell operation. Then we'll be mostly discussing about how this IV characteristics, then this modeling of PV panel, then we enter into the systems and mismatch losses and everything. Okay. Yeah. You can always interrupt me whenever there is a doubt or concern that you want to clear up. Our participants or the organizer, request the organizer, if there are any questions pop up in the chat, please let me know so that I can clear then and there itself. Well, so since we're talking about energy, power, that is electrical power, so I thought it's good to start with what is work, what is energy, and what is power. So we all know that work is involving two things, force into distance. If you want to move something for a distance of 5 meter or 4 meter, so definitely you need certain force and also some mass. So for example, if you want to move 20 newtons, if you want to use force of 20 newtons and push an object 5 meters, then the work is 100 joules per work. What about energy? Energy is you should be able to have that much of energy to do that work. So basically the units are same. To do 100 joules of work, you must spend 100 joules of energy. Then here comes our interesting topic, that is power. So the power is the rate of work of, or how much you are, in what rate you are utilizing the available energy with you. So 1 watt is 1 joule per second. So if you take this second to the other side, so you get 1 watt second equal to 1 joule. And that's how you get 1 unit of power is equal to 3.6 megajoules. Okay. Please take a note of this particular value because we'll be revisiting this particular equation once again so that we can relate what is the energy available in the sun and then how it is related to the number of units that we can generate. Okay. So 1 kilowatt equal to 1 kilowatt hour, that is 1 unit is equal to 3.6 megajoules. Okay. Now, there are different energy conversions available out there, but we are very much interested in electrical energy. So, in what are the different ways of conversions possible to get electrical energy? So, we start with the chemical energy into thermal energy, then thermal to mechanical, then mechanical to energy, and you can look at the efficiencies. So, it will come around 45 or 50, roughly 50% of efficiency. But there is other way. You can directly get electrical energy from chemical by using fuel cells, and efficiencies are around 60%. Okay. And there is another way, that is gravitational or hydrodidal. You can use the gravitational energy and you can create that difference in heights, and that you can convert that into mechanical energy and mechanical energy to electrical energy. That is also possible. And we also know about the nuclear. So nuclear fusion reactions can generate a lot of heat. That is thermal energy, then thermal energy to mechanical energy, then mechanical energy to electrical energy. And here comes our renewable energy sources, that is wind and solar. And we know how to do that. So wind to mechanical and mechanical to electrical. And from solar, it is possible that you can go generate a thermal energy from thermal into mechanical, mechanical to electrical. That is also possible. But there is a possibility from solar to electrical, and that is nothing but your PV. We'll be talking about this in a couple of hours from now. So just to give you overall idea, like how many kinds of PV panels are available out there, and what are their efficiencies. You can have a look at this particular figure from National Renewable Energy Laboratory. So that is NREL. You can follow this page if you are interested in working in renewable energy. So it will give you all the data, all the products, and whatnot. So you will find a lot of interesting stuff here. So if you look at these colors, so these are multi-junction cells, and this color that is blue, that is crystalline silicon cell, that is monocrystalline cells. And there is something called green. They are thin film technologies and emerging PV technologies as well. So if you look at multi-junction cell efficiencies are always higher than the blue ones. You look at this efficiencies around 46%. And every point in the chart tell you who has come up with this one. For example, if you take at this point, at this year, NREL has proposed one multi-junction cell. So every point tell you either the laboratory or the institute who has proposed that particular PV panel and what are those efficiencies as per the year. So you can get huge information here. Now in this presentation, we'll be talking about not one in particular, but we'll be discussing how multi-junction is possible, how to select this particular semiconductor devices and whatnot. So I'll be talking about the basic uh, research and challenges in collecting the components and in designing the components as well. Okay, so there'll be a little bit mathematics involved here and there, but don't worry about that one. So I'll be uh, going through in a better way so that people can be comfortable. Okay, so this is the electrical data of a PV panel. When you purchase a PV panel, this is what you can see at the back side of the panel, or even you will be. I'm sorry. Yeah. So basically, I want to start with what is this STC. So all these ratings, whatever given, it is valid for standard test condition, which says irradiance 1000 watt per meter square and module temperature 25 degrees centigrade. I think this is quite straightforward. Everyone know about this. But what are these two terms? Irradiance and AM, that is air mass 1.5. So to know that, we need to know something about solar, sun first at the instant. Then we will talk about what is this power, maximum power, open circuit voltage, short circuit current, and whatnot, everything. So first we'll talk about what are these standard test conditions, and that's how we proceed further. Okay. For that, we need to know about the significance of solar. So as you all know, sun is the source of everything. Sun is the source of wind. Because of sun, there is a wind. Because of sun, there is hydro. Because of sun, there are many things. And we have seen all the conversions that is possible to get an electricity from that. So it is good to know what is sun and what's happening there. So basically, a sun, what's happening there is a fusion reaction is happening there, where hydrogen is converted into helium, and as a result you get around 20 million degree Kelvin. But fortunately, we are not getting that much heat at the surface because most of the heat is absorbed by H ions, and you can see that at the surface it is around 6000 Kelvin, which is close approximation to black body radiation. Okay, so whatever the heat generated there will be radiating into the space. Okay, so how it radiates and what is the energy available in that? Okay, some fusion reaction is going on at the sun. Why do I care? So why you have to care is when it radiates, you get a lot of energy. What is that energy and how can you tap on that energy? So that is the main focus here. Okay, who gave that formula? It's Einstein who gave that formula. The energy associated is E equal to mc square, where m is the mass lost. But with fusion reaction, there will be some mass losing by sun. So if you calculate that one, it will be roughly 3.8 10 to the power of 20 megajoules is available at the sun. Okay, what does that mean? we know that we have seen 1 kilowatt hour or 1 unit is 3.6 million joules. Then what will be the how many units you can generate? And if you are curious, it is like total installed capacity in India is 386 gigawatt. I think this is with respect to 2019 March. That's what I looked at. But there may be an update. I'm not sure. So that will be roughly around 3.8 into 10 to the power of 9 kilowatt. Okay. So now you can imagine how much energy is available out there. But we are not getting this much of energy because we are quite far away from the sun, and there will be some losses in between. So we look at how much energy exactly we are receiving. Okay, for that we need to know that there is a fraction of radiation that is coming out of the sun is received by the earth. We'll see what is that. Okay, so to generate energy from sun, which is quite abundant, there are some factors affecting that. The first one is the spectral content. So what is the amount of radiation we are receiving? That is the first thing. Then what is the energy in that particular spectral content? For example, if there is gamma rays, X-rays, infrared, everything is available, but we are getting only visible. So in that visible range, what is the amount of energy that will be receiving by Earth? And then we know about the panel direction. We have to keep the panel in particular direction. So that direction also matters. And also the location where you are talking about. Are you talking about India, that is especially Tirupathi, where the current event is happening? Or are you talking about America? Are you talking about Australia? So it depends on various factors. So various factors will be I think you will not be able to seeing the screen. I'll be sharing it again. Um, can someone let me know if the screen is available? Hello?
Now it's coming, sir.
Okay.
Sir, can you do this slideshow, sir?
Yeah, it's already there, I think.
Yes, sir. Now it's coming, sir. Thank you, sir.
Okay. Yeah. Fine. So we'll talk about all these things in a while in a greater detail. So we know sunlight is emerging as an electromagnetic wave, and we have a lot of wavelengths available. As I said, there will be gamma rays, X-rays, UV rays, but fortunately we'll be seeing only visible spectrum. Okay, so in that visible spectrum, we need to know what is the amount of energy available there. Okay, for that we need to convert that energy in terms of electron volt. So why we are interested in calculating energy in terms of electron volt? I'm sorry. Why we are interested in calculating the energy of a photon in electron volt? So we talked about joules, and now he's talking about electron volt. So the electron volt is important in deciding the semiconductor material. Okay, so I'll be talking about dots here and there, and finally I'll try to join all the dots here. Okay, so by using Planck's constant, we can calculate the energy associated with the individual photon. That will be depending on the wavelength. So if the wavelength varies, then the energy associated with the photon available in that particular light will be varying. So that's how you get uh, this constants. So I'm not going into the math. So I'll be talking about visible spectrum. Okay, so we know that it starts from 3.8, that is roughly zero point 0.4 micrometer, and see the photon energy is 3.09 electron volt. And for the wavelength of 0.7, that is the red light, so you'll be getting 1.7 electron volt. Okay, yeah, I think again there is an issue. I'll start broadcasting again. Sir, is there any reason behind this? Is this a problem from my side? Why it is stopping at every 10 minutes or something?
Uh, so not like this. So I request participants please turn off your video because the video takes more pixels, more packets, data packets.
Okay.
Please cooperate with us.
Okay.
So now it's visible, sir. Thank you, sir.
Yeah. If someone is wondering what is this electron volt, that means if you want to push an electron against 1 volt, for example, if there is a barrier of 1 volt, then if you want to push an electron above that one, the energy required is 1 eV. So that will be roughly 1 electron volt equal to 1.602 into 10 to the power of minus 90 joules. Okay. So the important takeaway from this slide is every photon available in the visible spectrum has some energy. Okay, and that energy that's what we calculated here.
Hello.
That is in blue light, it is 3.0995 electron volt, and in the red light, it is 1.77 electron volt. But in between, it will be ranging from 3 to 1.7. So that's the amount of electron volt available for one photon. Okay, just available for one photon. Then what is the number of photons that is available that we need to calculate now? Okay. For that we need to know the photon flux and photon power density. So the value we have seen that 3.77 electron volt, that is the energy available in one photon. But we will be receiving a bunch of photons. So for that we need to define these constants, that photon flux, which will tell us about how many photons you are receiving per second in a square meter of area. Okay, so I'm not going into too much of mathematics again. So let me tell you, if you say that if it is 3 into e to the power of 21 photon flux, that's the energy, then will be power density will be 961 watt per meter square. Now we'll be able to relate what is this watt per meter square, how it is coming from. Okay. So the standard operating condition tells you it is 1000 watt per meter square. This is where it is coming from. So it is coming from because there is an energy at the sun, and the sun is radiating into the space. Unfortunately, we are not receiving all the radiation, but we'll be receiving only visible spectrum. In the visible spectrum, there is a photons of energy. Each photon has certain energy from starting from blue light to red light. And then from blue light to red light, there will be like one photon having that much energy. But if there is a bunch of photons coming to you, then what will be the energy with that one? So that is why you are getting 1000 watt per meter square as a standard operating condition. Okay. But if you look at if the energy of the photon changes, see the variation in the power density. Okay. So everything is important. How many photons you are receiving and what is the energy of the photon. I just changed one value here. So I just changed 2 electron volt to 1 electron volt, but I'm receiving same photon flux. Let's see the power has reduced a lot. Okay. And similarly, if I reduced 3 e power 21 to 3 e power 20, and you can see the variation in the amount of watts that you'll be receiving in a 1 meter square area. So that's the significance of the photons that you receive. Okay, whatever the photons you receive is really a huge thing to decide on the panel construction. Okay. Now coming to the actual thing, that is spectral irradiance. So we talked about individual photons. In the individual photons, then if a bunch of photons of same wavelength is coming, but we'll be getting from 0.3 to 0.7. So we have to integrate everything to get the total energy associated with every photon of every color. So blue light, there is some bunch of photons. The red light, there is bunch of photons. Violet, there is some bunch of photons. So if you want to calculate the energy, then definitely you have to go for integration. So with that integration, you'll get the total energy associated like this. So if the temperature of the black body varies like this, if it is 1000 and from wavelength 0.1 to 100, this is how the watt per meter square changes. Okay, but we know our sun's radiation is around 6000, that is 5777 Kelvin, and we are receiving only in this range, and that is why we are taking that as 1000 watt per meter square. Okay, that's about irradiance, how you are getting that one. But again, we are having a distance from the sun, okay, and the radiation varies with inverse square law. So for example, at the surface there is a huge energy, but by the time it reaches certain distance, it will come down, because in the previous slide, if you have seen that at the surface, see the energy, it is 10 to the power of 8 watt per meter square. But this is not we are receiving, because we are far away from that, because of this formula where h is inversely proportional to the distance between the two bodies. Since we are quite far away from the sun, and this inverse square law comes into picture, and that's how different planets receive different watt per meter square. Okay, Earth will be receiving 1366.1 watt per meter square. Wait, we were discussing that it is 1000 watt per meter square, but actually we are getting 1366. So what happens to that 366? That is because we have some effects. That's wobbling effect, we'll discuss in a while. And also there will be atmospheric pollution everywhere. That is also causing to reduce this 1.3 kilowatt hour to 1 kilowatt hour or less than that one. So we'll discuss that in a while. Okay, so the power variation due to elliptical orbit itself is 3.4%. And also there will be atmospheric effects. So there will be ozone layer, upper dust layer, air molecules, water vapor, lower dust molecules. All these things scatters the light, and finally you get some reduced amount of light that is coming to the panel. Okay, so these and all matters, everything atmospheric effects, whatever I discussed here, that is ozone layer, upper dust layer, and the percentages are clearly shown here. And there will be scattering. Because of the scattering, it loses some photons. So finally, the amount you receive is less than 1366 watt per meter square. Okay. Then we'll talk about air mass. What is this air mass? So air mass is the ratio if you receive the light directly to a point, but if you receive the same light from an angle. So that's the difference. This ratio of light intensity that you receive if you are straight ahead of that point, or if you are at an angle at that point. So that ratio gives you air mass, because we never expect always your sun is directly on your head. So it will be moving here and there, even including the total of take the total Earth. It is also because it will be having some angle variation. So that is why we generally go for 1.5 rather than 1, because we cannot expect sun is always straight to the panel or straight to the earth. So it is moving here and there. So average, it is taken as 1.5. Okay. If you see, like, for example, if there is a light coming here, it is straightly here. It will be 1 here. But if your location is here, then it will be scattered like this. So that is why most of the time it will be taken as 1.5 as standard operating condition. But if you are wondering what exactly is it, then you have to find out the angle. Then you use this formula, you will get what is the exact AM in your particular location. Okay. But most of the panels are tested with 1.5. Fine. So we covered most of the part.
Feedback.
Sorry.
అప్పుడు ఈ క్వశ్చన్స్ కూడా వస్తాయి కదా దాంట్లో ఫీడ్బ్యాక్ కూడా
I think this time the issue is from my side, because any doubts so far, organizers? Anything in the text or chat?
Sir, up to now, no questions, sir.
Okay, ma'am. Give me a second. Yeah. Okay. So if you take AM as 1, you will be roughly receiving this much of energy, that is 2 kilowatt hour, 2 kilowatt per meter square. If it is 1.5, you will be restricting to 1.3 or 1.5. So average, it is area under the curve. So it is going here and coming down. So you have to take area under the curve. So that's why it will be considered as just 1 kilowatt watt per meter square. And coming to the position of the Earth. So we know that our Earth is tilted like this, and then it started rotating in elliptical orbit. And because of that, it will be having a wobbling effect. What does that mean? So the convenient reference, if you take Earth is fixed, Sun is moving, so you will be talking about this variation from June to December. We'll see that one in a while. Okay. So for example, if your house is here, in June, your sun path will be like this from morning to evening. But in December or January, it will be like this. I'm sorry, I don't know what's happening here. I suspect it's because of too many
It's
GIFs.
visible, sir. It's visible for us, sir. PPTs are visible for
Okay.
us.
Okay. Maybe because of so many animations, sometimes it is shutting down. I shouldn't have used so many animations. Sorry about that. So, to summarize whatever we discussed so far, there is so much of energy available at the sun, and but unfortunately, we are receiving that one. There will be like too many impacts on that one. Now we come across what is the total amount of radiation that will be irradiation that will be receiving at the particular location. But above that, there is something that you need to take care about the position of the angle. So in which angle that my uh, panel should be placed. For that, we are trying to get the background why I have to keep that angle in this position. So that's the reason behind going to this different angles. That is the declination angle, elevation angle, and azimuthal angles. So basically, what I'm trying to tell you is the sun is not taking the same path every day. For example, if it is morning 6 o'clock, the sun rises and sun sets. If you look at in December, it will be some location. If you look at in uh, June, it will be in some other height. So the height variation. So that is what the declination angle tells you. So in June, you will see it is at the maximum height, but in December, it will be at the lowest height. So it may not cross this line, but it depends on the location. If you are in southern hemisphere or northern hemisphere, or if you are near to the poles, then it happens like this. Okay, so these angles are very much important to decide. Basically, what I'm trying to tell you is these angles are very much important, so that by using these angles you'll be able to decide what should be the inclination of my panel and in what direction that I should keep the panel. We'll come to know that in a while. Maybe this will be better for you to get an understanding. So today, that is October 19, your sun's path is like this at Tirupati. Okay, in June, sun will be taking this path. So it sun rises here and it goes here like this. But in by the time you reach December, it will lower. I mean, you don't find sun at exactly above your head in December. It will be somewhere at an angle. Only in June, you will be seeing your sun is positioning directly above your head. That is nearly 90 degrees, not 90 degrees. So this graph tells you how it happens. So it starts at east by 12 in December. The angle at which you see the sun is around 55 degrees, not 90 degrees. You see nearly 90 degrees only in the month of April for this location. Okay, for this location, that is Tirupati, right? So these charts are available online, so you can go and have a look at it. Now, what I should get from this chart part, like why I am so much worried about this one. Now, if you see in January or in December, you see the angle is 50 degrees here, but the same at 12 o'clock, the angle is around 90 degrees. So I need to take care of these things because it is very much important that my panel should be facing the sun. Okay, but I cannot change the panel for every day and every hour. So is there a method that we can get rid of all these things, or is there a method that I can take care of all these variations? You see that in a while. So there will be again some mathematics involved here. For example, your location is latitude north. I think if I'm not wrong, at Tirupati it is latitude 13 degrees centigrade. So you have to place, I mean, the animation shows here it is latitude 15 degree north. So that means you are in southern hemisphere. So most of the time, your sun will be in the north side. So it won't go beyond that one. Let's try to play this one. So this graph tells you what is the incident power. The blue one tell you what is the incident power. And if you change the panel direction, for example, this module power, the green one. So when I'm changing the angle, I mean, when I tilt this panel, you can see how the power varies in the module. Okay. So my tilt angle is 31. That's how it changes. Okay, so the position at which the panel should be placed is calculated here by using all